Okay guys, let's go ahead and go over the warm-up questions on my screen. Hopefully you have already answered these in MyOpenMath, but if not, you definitely need to make your way there to answer these questions for your warm-up today. And then as soon as we're done talking about the warm-up, we're going to get into our notes, talking about Newton's second law in terms of calculations today. And then you do have an assignment that you'll be working on for the end of the period or possibly for homework 301.2 second law and FBD problem set that's due by 11:59 p.m. tonight. So the warm-up says, how does the force of gravity compare for a 3-kilogram cat versus a dog with twice as much mass? And then the second question says, how do their accelerations compare if both fall to the floor from the arm of a couch? So let's start with the first question. How does the force of gravity compare for the 3-kilogram cat versus a dog with twice as much mass? You guys did calculations yesterday for force of gravity, which by the way is weight. So I'm asking you, how do their weights compare? 1/2. Sorry? Yeah, the cat would have 1/2 as much force of gravity acting on it compared to the dog. Okay, and so mass and force of gravity are going to be directly proportional to one another for a given gravitational field. So as long as you're on Earth, you know, it will be true. Obviously, if you change the field, that's different. We looked at that yesterday. So again, you should say that the cat has half as much force of gravity acting on it as the dog, or maybe the dog has 2 times as much as the cat, however you want to word that, that's the same thing. The second one says, how do their accelerations compare if both fall to the floor from the arm of a couch? Yes, sir?
Is it equal?
They are equal, yes. Okay, they would be equal. Again, this is last unit. Okay, their accelerations will both be negative 9.8 meters per second every second, or negative 9.8 meters per second squared. Okay, that is free fall. So again, please make sure that you have those answers, and we're bringing in stuff from last unit as well. As I said, we're going to take some notes today, so let's go ahead and get to it. I showed you this slide yesterday, but I figured we would start here because we're going to be talking today about how we can detect when forces are acting on things, because sometimes those forces are going to cause our objects to change their motion. We're going to have objects that speed up, we're going to have objects that slow down, we're going to have objects that turn, all because there are forces acting on them. Okay, again, there's always forces acting on us though, so sometimes those forces don't affect our motion at all. Right now, we all have force of gravity acting on us, and yet we're not speeding up or slowing down or turning. But again, we're going to get into why as we add some numbers to this stuff. So again, you can write this down if you want. You guys saw this slide yesterday. If you want to follow along on your own screen, I'm currently on slide 23, and you're welcome to open up and follow along as we go through the notes. Okay, so Newton's second law. Newton's second law states that a net force causes acceleration. More specifically, it states that the acceleration of an object is dependent upon 2 variables, the net force acting upon the object and the mass of the object. And that law can be summarized with the equation that you see at the bottom of my screen. And it's one you probably already recognize. Usually you'll see it more colloquially written as F equals ma. But technically it is F net equals ma, or net force equals mass times acceleration. That is Newton's second law, okay, and it's our second equation for this unit. We talked yesterday about our equation for force of gravity being mass times gravitational acceleration. Okay, F net is mass times acceleration, and it's not necessarily gravitational acceleration this time. It's going to depend on the scenario that we're looking at. Okay, so again, Newton's second law states again that the acceleration of an object is dependent upon 2 variables, the net force acting upon the object and the mass of the object. And please write down that equation. When we use this equation, our net force will be measured in newtons, just like yesterday. Forces are measured in newtons. Our masses, just like yesterday, need to be measured in kilograms. So again, if you see a problem and they're telling you a 500-gram baseball is, accelerating at a rate of 5 meters per second squared, you're going to, before you calculate that net force, have to do a conversion and get that baseball's mass into kilograms. Okay, so please make sure that your masses are in kilograms. If you solve for mass, your units will be kilograms. Okay, and then your acceleration units are meters per second squared. Okay, so those units, make sure that you are familiar with those as well. All right, so let's go ahead and try an example calculation. This one says, what amount of force is required in order to accelerate a 25 kilogram object at 5 meters per second squared to the left? Again, we're going to label our given information. We have a mass of 25 kilograms. We have an acceleration of 5 meters per second squared to the left. I went ahead and labeled that as negative 5 meters per second squared. Because again, acceleration is a vector. It has a direction. It says in the question, to the left. So I'm going to call that the negative direction. Some of you missed this yesterday, but in case you weren't already aware, mass does not have a direction. Mass is scalar. There was a question about that in your assignment yesterday. That's why I don't have a sign in front of that. It's just 25 kilograms. Okay, so we have our mass, we have our acceleration, we are being asked to solve for force, and it will be in newtons for your unit. The equation F net equals ma is what we will use, and if we substitute into that equation, it's just going to be 25 times negative 5. 25 times negative 5 is negative 125 newtons. A newton, by the way, and you can see this right here, is a kilogram times meters per second squared. It's the same thing. If you need to make a note of that, you can, but that's why those masses have to be in kilograms, because a newton is a kilogram meter per second squared. And that's how the units cancel as well. So again, my force, when I multiply that, negative 125 newtons, or you could write that as 125 newtons to the left. Okay, does anybody have a question about this calculation? I think you'll find the math, at least thus far in this unit, to be pretty easy. Hopefully you agree with that. All right, let's look at another one. What is the acceleration of a 0.5 kilogram toy car that rolls rightward down a ramp with a net force of 2.5 newtons to the right? Again, I am given a mass. I am given, this time, the force is given to me, 2.5 newtons to the right. So my net force is positive 2.5 newtons. Again, I'm going to go ahead and call the right direction the positive direction for the purposes of my calculation. And my unknown, what I'm trying to solve for, is acceleration. Again, same equation, F net equals ma. So if I substitute in, this time I have to do a little bit of rearranging in order to isolate my variable. When I plug in, I end up with 2.5 equals 0.5 times a. I left my units in there so that you could see how we end up with this. But whenever I want to isolate that variable, we have to divide both sides by 0.5. When we do that, 2.5 divided by 0.5 gives me an answer of positive 5 meters per second squared, or 5 meters per second squared to the right. Again, because a newton is a kilogram meter per second squared, when I divide by kilograms, those cancel, and this is my remaining unit. Does anyone have a question about this one? Okay. This question says, so sometimes you have a word problem, okay, with all the information there, and sometimes you're going to have a free body diagram or a graph or something else given to you instead, and you're going to have to get information from that diagram or graph or whatever it may be. This one says, if the mass of the box below is 2 kilograms, what is its acceleration? Okay, well, the question only gives me one piece of information, and that's a mass. However, the picture gives me a second piece of information, and that is the force acting on this object. Okay, and so if I want to do this, my first step is going to be to find the net force. Well, I only have one force, so that's handy, because that means that is my net force, 3 newtons to the right. Okay, so I have my net force. Step 2, find my acceleration. We're going to solve. Okay, I know my equation F net equals ma, and I just need to substitute into that because I know my net force is 3, and I know my mass from the question is 2. So I have 3 equals 2 times a. Again, if I want to solve for a, I need to isolate that variable, dividing both sides by 2. 3 divided by 2 is 1.5 meters per second. And again, the direction's not written in the question, but I can see it in the picture, to the right. Acceleration is a vector, and your acceleration will be in the same direction as your net force. Okay, if you need to write that down, you can. But your acceleration will be in the same direction as your net force. So if your net force is to the right, your acceleration will be to the right. If your net force is up, your acceleration will be up, so on and so forth. So again, sometimes it's written out in words, sometimes you're going to have to look at a diagram of some kind. This says, what if the mass is doubled? Okay, if the mass was doubled, what do you think that would do to my acceleration? Turn and talk to your neighbor for a moment. You have 23 seconds to discuss with them. If my mass is doubled, what happens to my acceleration? How does it compare, is what I'm asking you to talk about. Oh, my sound is off. Sorry. All right. Let's see. Mason, what'd you come up with?
Well, if you do the equation, it's faster, but you would think it would be slower.
If I double the mass.
Oh, double the mass. I was thinking about the newtons. It would make it slower.
Yeah. Okay. If I double the mass, just looking at the equation, since I ended up doing 3 divided by 2, I'd be doing 3 divided by 4 instead, right?
Yeah.
Okay, and I would end up with a smaller acceleration. So the rate at which the acceleration occurred would be smaller. Again, you can recalculate it with that in there, and you would get half the amount of acceleration if you had double the mass. That makes sense. Think about it logically. Okay, if you push with the exact same amount of force on 2 different objects, and one of them is a lot heavier than the other one, which one do you think is going to accelerate more, the lighter one or the heavy one? The lighter one, right? You would expect that to happen. That's exactly what you see, and you can see it mathematically as well. That you're going to get, if you have double the mass, you're going to get half the acceleration of the object, which means, of course, that your mass and your acceleration are inversely proportional to one another. Okay, you need to be able to see those types of relationships. That type of question, by the way, was the most missed question on your test that you had the other day, was the one that asked about, hey, if you, like, I think it said if you double the height or something, or quadruple the height, I don't remember, like what happens to the final velocity. That was the one that y'all missed the most. So we need to make sure that we are doing or understanding these relationships. And you can do this. You can plug in numbers and see what happens to it to help you answer questions like that. Okay, if you're not sure about the relationship, but hopefully you can see the relationship by just looking at the equation. Okay, you can see it here because for a given force, these two things would have to multiply to give you this value, and if this is the same amount, then a smaller mass is going to be a larger acceleration and vice versa. Yes, sir?
Does this test on a unit page?
It doesn't. It's so short that we didn't put one together. There will be an opportunity for bonus points, but it's not going to be through a unit summary. Okay. All right. Questions about this? Okay. So again, half the acceleration is what the answer would be for that. All right, here's another question. How much force is needed to accelerate a 14,700 Newton car from rest at positive 2 meters per second squared? Again, labeling things or starting with a diagram might even be helpful. We're trying to figure out how much force is needed. Okay, I did go ahead and label the weight of my car as well as the support force from the road or the ground, which we don't really need to worry about those numbers just yet. I'm really just looking for this one. But the information I've been given is the weight of my car. If you read a question and it says, you know, a 700 Newton man or a 5 Newton apple or whatever, okay, cat. Whatever it says, if it says, you know, a 14,700 Newton car, it is telling you the weight of that object, okay, if it's worded like that. So they have given me the weight of the car. And I know that weight from yesterday is Fg, okay, and I know it's a negative force because it's toward the ground. And so I went ahead and labeled it negative 14,700 newtons is my weight. The other piece of information they gave me was an acceleration of positive 2 meters per second squared, and I am looking for the amount of force, but in order for me to solve for force, remember I need mass times acceleration, and right now I don't have mass. But yesterday we found out that if we know the weight, we can find the mass, or vice versa. So you might see a question like this, where they give you a weight and you have to find the mass so that you can then solve the problem that you're actually trying to find, which in this case is the force that would be needed to cause the acceleration of this car. Okay, we're going to solve for mass first, and then we'll get force, and we're going to solve for mass using the equation from yesterday, F sub g equals m times g, and then we can use F net equals ma once we know what the mass is. Okay, so plugging in, I have this, negative 14,700 newtons equals mass times gravity. So m times negative 9.8. Divide both sides by negative 9.8, and I'll get my mass. The mass of my car is 1,500 kilograms. Okay, so now that we know the mass of the car, we can solve for the force required to make that car accelerate at a rate of 2 meters per second squared. Okay, and here is how you would do that. Here's my force equals 1,500, that's the mass I just found, times 2 meters per second squared. Of course, 1,500 times 2 would be 3,000, and it would be positive 3,000 because it will be in the same direction as my acceleration, and it said positive 2, so I've got positive 3,000 newtons would be the force. I could even label it on my diagram up here. Okay, so don't use this as your force. That is the weight. So if the question is worded like that, they're not telling you that's the force that it's using. It's calling that a property of the car, 1,400 Newton car. Okay, so that is the weight of the car. So you got 2 steps if they do that. Okay, does anybody have a question about this particular problem? Okay. All right, this one says, what happens to acceleration if you push with twice the force? Again, as a reminder, 3,000 newtons caused 2 meters per second squared acceleration. What if you pushed with 6,000 newtons instead, twice the force? Again, turn and talk to your neighbor and talk about what you think would happen if you push that same car with 2 times the force. You have 20 seconds to discuss. All right, Kimberly, what'd you and Braden come up with? What do you think? Yeah, again, think about it logically. If you push it harder, you would expect it to accelerate more, and that's exactly what you're going to see mathematically as well. Okay, you can also solve it though if you're not sure. Again, the car still has the same mass. Now we're just looking at pushing with twice the force. You can figure out what that acceleration would be. 6,000 divided by 1,500 would tell you your acceleration would be 4 meters per second squared instead of 2 meters per second squared. Okay, and so you would have twice the acceleration, and again that means that the force and the acceleration are directly proportional to one another. Again, that's the type of question that you guys were struggling with the other day, so I just wanted to go back over that kind of proportional reasoning. You should be able to do that with any variable in any equation. Okay, and again, you can plug in numbers if you need to, or you can just look at the equation and say, hey, you know, if I double this number and my mass stays the same, I will have to have double the acceleration. You can see that without having to plug numbers in, hopefully. But again, if you need to, do this and see what happens. All right, so 2 times the acceleration. So again, we just looked at these relationships. I've added some words up here. Instead of just saying the acceleration is affected by, I've said what the relationships are. So the acceleration of an object is directly proportional to the net force acting upon the object and inversely proportional to the mass of the object. We just saw both of those relationships. So this would be a better wording. But again, this is already defined by the equation. But if you want to write it down, please. That means larger net forces cause larger acceleration, so long as you're comparing equal masses, and that larger masses will accelerate less, Okay, again, as long as you're comparing equal forces. So we just looked at these different relationships, but if you want to add it to your notes, the acceleration of an object is directly proportional to the net force acting upon the object and inversely proportional to the mass of the object. This, by the way, is slide number 31 if you want to come back to it later. Okay, I just really want you to write down the relationships. You can write down what it means here as well if you like. Okay, again, net force and acceleration are directly proportional. Acceleration and mass are inversely proportional to one another. So here's a question. What if the net force acting on the object is 0? Okay, we have the equation. Okay, so what do you think would happen if the net force was 0? What would the motion of that object look like? Anybody have any thoughts?
Zero would be falling.
Sorry? Never mind. That's okay, but like think about it mathematically. If this is 0, the object still has mass, what's your acceleration have to be? 0. Okay, so if you have no net force acting on the object, 0 net force, it means that object won't accelerate. It doesn't mean it's not moving, although it could. Okay, but it means that if it is moving, it's moving at constant speed. Okay, I've used the word net force a lot, but I haven't actually defined it for you yet because everything we've looked at, I've just given you a number. Okay, but net force, the net force acting on an object is the sum of all forces acting on that object. Now, forces are vectors. Direction matters. When you add forces, you must examine horizontal and vertical forces separately, and you're going to find a net force in the x direction and a net force in the y direction. So I have these two guys playing tug of war and they're pulling, and I'm going to assume that they're pulling with equal and opposite forces so that I have a diagram that looks like this. I'm just showing the forces acting on my rope. Okay, and so I have 20 newtons this way, I have 20 newtons this way. And so if I wanted to solve for net force in this particular example, again it says it's the sum of all forces, but again remember forces are vectors. So because one of these is to the left and one of these is to the right, when I add them I have negative 20 plus 20, or plus positive 20 if you want to put the sign in front of it. But of course, if I do that, I get 0 net force. And in this particular example, I didn't even show any forces in the y direction, so based on my diagram, I'm going to say there aren't any. Okay, this is somehow a massless rope or something. And so that would be my net force in the y, based on the fact that I don't have anything there. So I really wouldn't be examining the y direction in this particular problem. I'm just looking at horizontal because that's what is labeled for me there. Okay, so again, that's net force, the sum of all forces acting on the object, taking into account their direction. So I asked you a question a moment ago about 0 net force, and we said that that means it wouldn't accelerate. And I've got 4 different diagrams here, and I've labeled them A, B, C, D. And it says, which of the free body diagrams below shows an object with a net force of 0? I'll give you a moment to look at it. Okay, but look at A, B, C, and D and see if you can figure out which one or which ones would have a net force of 0. Okay, and you can talk to your neighbor about it as well if you like. And did you find one? All right, which one?
I said,
Yeah, go ahead.
did you see me?
Yes.
A and D.
A and D, perfect. Okay, A and D both have a net force of 0. I told you, now for D, I told you have to examine vertical and horizontal separately. So vertically I have 8 and negative 8. Horizontally I have 5 and negative 5. It doesn't matter that they're not all the same as each other. I'm just looking at horizontal, 5, 5. Vertical, 8, 8. They don't have to be all the same number. Okay, but they do need to cancel out in order for my net force to be 0. And of course A you can see a little bit easier. B and C, on the other hand, would have net force and thus would accelerate, whereas A and D would have either constant velocity or 0 velocity. I don't know which, based on that diagram alone. Okay, but again, you should be able to look at a free body diagram and determine the net force or determine whether it would accelerate or not. By the way, what would the net force be for object B? I heard somebody say it over here. 3 newtons, and I need a direction. Down. Okay, so again, that's how you determine your net force. Okay, so it's just sum of the forces. All right, So again, net force must be calculated, and you probably already wrote this down, separately for horizontal and vertical directions. Forces in opposite directions can cancel out either in part or in total if they're exactly the same. Forces in the same direction add together. If a net force exists in both the horizontal and vertical directions, then a resultant net force is drawn at an angle and calculated using Pythagorean theorem or trigonometric functions. We're not doing that yet, but that is going to happen in the next part of this unit. You are going to see sine, cosine, and tangent, but not today. It'll be after this test because I told you we split the unit in half. Okay, but it is coming, so get ready. All right, zero net force, and we already determined this a minute ago, tells us that the system will not experience acceleration. That means that it either stays at rest or it moves with a constant velocity because the acceleration is zero. So if your net force is zero, your acceleration is zero. And that doesn't mean you're not moving, it just means that if you are moving, it's at a constant speed. Okay, a non-zero net force, so when they don't cancel each other out, it tells us that our system will experience acceleration. That means that we're either going to speed up or slow down, or we're going to change direction because our acceleration is not zero, because our net force is not zero. So we're going to have some kind of non-zero value for net force, and thus a non-zero value for acceleration, which again means that our velocity is changing. So again, we can tell the acceleration of an object from its net force. That's all we can tell. I don't know which way the object is going. I don't know, if I don't know which way it's going, I don't know if it's speeding up or slowing down. So there's not a lot you can tell other than, is this accelerating? And you can tell the direction of the acceleration. Okay, so let's take a look at that. Which of these could be at rest? Which one could be just sitting at rest? Yes, Nate. A could be sitting at rest. My forces are all balanced. C could be sitting at rest. My forces are balanced. Okay, B and D, not sitting at rest. Okay, because I have my forces do not cancel out. Okay, my net force in those two is non-zero. It's something else. For B, it's 5. For D, it's 20. Both of them to the right. Okay, the second one says, which could be moving at a constant velocity? What do we think there? Could B be moving at a constant velocity?
C.
Morgan's shaking her head no. Okay, why can't B be moving at a constant velocity? Because it has a net force, right? That means it's going to accelerate. Okay, the answer to the first question and the second question is exactly the same. Which could be at rest? You guys already told me A and C, so guess what? Which ones could be moving at constant velocity? A and C. Okay, those are the only two that aren't accelerating. And again, I don't know if they're at rest or if they're moving based on just this picture alone. But either way, I know that they're not accelerating. So at rest or constant velocity, still the same answer, A and C. Okay, which direction is object A moving? Do you know, Brayden?
No.
I don't know either. Okay? You can't tell. Unless the question tells you something about it, you cannot tell. In fact, I don't even know for sure that it is moving. Okay? When you look at that diagram, that object could be moving up, down, left, or right, or not at all. Okay? All I can tell is it's not accelerating. So I don't know if it's moving. If it is moving, I know it's constant speed, but I don't know which way, unless the question tells me something else beyond what I can see in that picture. Oh, wait, I have them up here. A, C, and cannot tell. Okay, so again, we just went through each of those. Which of these could be moving to the right? What do you think, Gavin?
B and D.
Maybe. If they are, they're getting faster. But I don't know if any of them are moving to the right. Just like I said a second ago, I have no idea. Okay, they could all be moving to the right. Oops, I didn't mean to click that. Okay, or none of them could be. I don't know. All of them could be with the way it's worded, which could be all of them. They could be. Again, I don't know with the information I have. You cannot tell. Again, write this down in your notes if you need to, but you cannot tell the direction of the object's motion if you look at a free body diagram. All you can tell is the direction of the acceleration. Again, if B and D are moving to the right, they're getting faster. If they're moving to the left, they're slowing down. Okay, I don't actually know which way they're moving. I just know which way they're accelerating, which could be accelerating anything with a non-zero net force, which would be B and D. Those not just could be, those are accelerating. Okay, they are accelerating. And then find the net force for each. Well, A and C are 0. Okay, and I already talked about B and D. And the net force for B, vertically those cancel, but horizontally 15, negative 15 rather, and positive 20, we end up with positive 5, okay, for B, and then for D, obviously, we have just 20. Okay, so 5 newtons to the right here, 0, 20 newtons to the right here. So again, you should be able to determine net force from those diagrams as well. All right, guys, hopefully that made sense. I know it was a little quick, but your assignment for today is 301.2 second law and FBD's problem set. I'm going to encourage you to go ahead and get it opened up and get started on it. We are on advisory schedules, so you do have a little bit less time, but you still have 12 minutes, which should be plenty of time to ask questions if you have them, and a little bit of time to at least work through these with your neighbor. If you have questions as you're working, please let me know.